Welcome back mga kaaha! Today's episode, we have a fascinating topic for you. Fluid dynamics. We'll be delving into the concept of pressure at a point in a fluid. To help us understand this better, we have our expert Oyda Justine with us. Welcome Oyda Justine!
Thank you very much. It's been my honor to be here in your show.
So, Oyda Justine, let's dive right in. Can you explain to our viewers what pressure in a fluid means?
Sure, no problem. It's glad for me to explain to you what is the pressure at point in a fluid means. So, pressure at point in a fluid refers to the force exerted by the fluid on the unit area at that specific location. This force is perpendicular to the area and it's influenced by the factors like depth, fluid density, and gravity.
That's a concise explanation. Thank you. Can you explain to us and also give an example of how pressure at a point works?
Okay, sure. So, when we discussing a pressure, we are considering a normal force over a certain area. At a given point within a specific plate of the fluid of mass of interest. Now, the question is, will the pressure on the certain point vary with the orientation of the plate that passes through the point of interest? So, to answer this question, we can determine the pressure on the point within the specific fluid elements. In this case, a fluid elements will be the wave shape. So, as you can see, the shearing stresses will not be presented for the above situation. As a result, the external forces acting on the wedge are only due to the pressure and specific weight of the fluid. Now, for the above example, I am only considering the force in the Z and the Y direction for simplicity. So, to determine the force equation for the above example, we're gonna use the Newton's second law of motion, which is force is equal to the mass multiplied by acceleration. So that will be the formula that we will be applied. Now, in the equation 1 is the force equilibrium equation in the y direction. It states that the sum of the force in the y direction, or sigma Fy, is equal to the pressure force, or Py, acting on the surface. Now, the minus the shear force, Ps, acting on the surface, multiplied by the sin of the angle between the shear force and the normal to the surface, sin theta. This is equal to the mass density, or P, of the fluid multiplied by the area of the surface of delta x, delta y, multiplied by the acceleration due to the gravity, and multiplied by the depth of the fluid. So for you to understand furthermore on this equation, so let me break down the equation piece by piece. So the sigma Fy is the summation of the force in the y direction. So this means that we are adding up all the forces that are acting in the y direction. Now, the Py is the pressure force acting on the surface, and delta x and delta z is the area of the surface. So this is the area of the surface that are perpendicular to the y direction. Now, for the theta is the angle between the shear force and the normal to the surface. So this is the angle between the shear force and the line that is perpendicular to the device. I mean, perpendicular to the surface. Okay, now, for the P is the mass density of the fluid. We already know that. Now, for the G is acceleration due to gravity. And lastly, the Z is the depth of the fluid. Now, let me continue to explain the equation. So, Now that we are understand the individual terms in the equation, okay, so let's equal it all together. So in equation 1 state that the sum of the force in the y direction is equal to the pressure force acting on the surface minus the shear force acting on the surface multiplied by the sin of the angle between of the shear force and the normal to the surface. So this is the equal to the mass density of the fluid that multiplied by the area of the surface and multiplied by the accurate due the gravity multiplied by the depth of the fluid. So in another word, the summation of forces in the y direction represented by sigma Fy is equal to the product of Py and delta x and delta z minus the Ps and the delta x and delta s times the sin of theta, all of which equal to P delta x and delta y and delta z squared divided by 2 times Ay. Now for the equation 2, as you can see here, the summation of the force in the z direction denoted by the sigma Fz. This mean is equal to the product of the Pz and delta x, delta y minus the Ps, or density of the delta x and delta s, times the cosine of minus the y of delta x and delta y, delta z squared, all of which equal to P of delta x and delta y and delta z squared and divided by 2 times of Az, which is the acceleration in the y direction, and the y is the specific weight. So the above equation can be simplified when you take the consideration that the delta y is equal to delta s caused by theta delta and delta z is equals to delta sin theta. So this is the result of the following equation. So we have another 2 more equation here. So here in the equation 3 is the difference between the Py and the Ps is equal to the P times Ay and divide it by 2 and multiply by delta y squared. And for the equation 4 is the difference between the Pz and the Ps that is equal to the sum of the P times Az and y divided by 2 multiplied by delta z squared. So if you were to allow the delta x and delta z to go to 0, then the Py equals Ps and Pz equals Ps. Hence, it can be concluded that the pressure at the point will be Ps equals Py equals Pz. This means that regardless of the theta is the pressure at the point for a fluid at rest or in motion, it's dependent on direction as long as there is no shearing stress present. So according to Pascal law, if shearing stress is present, then the above statement will not hold true. This is because the x and delta y and delta z is typically represent small or infinitesimal change in the variables of x, y, and z respectively.
That's a clear illustration. Now, can you walk us through the mathematical expression for pressure at a point?
So, in mathematical expression for pressure at point in fluid is that the P equals Pgh, small letter, which is the P in the pressure at the point in Pascal, and the P and another P is the density of the fluid in kilogram per cubic meters, and the G is the acceleration due to gravity, which 9.08665 milliseconds per square. The H, which is represent the depth of the point below the surface for the fluid in meters.
Excellent, Kuya Jims. This formula practices a quantitative understanding. So now, how is this concept used practically?
Well, it is crucial in various fields like engineering, hydrodynamics, and even meteorology. And so it's understanding. So it's all based on understanding pressure as the point, help in designing structure, predicting weather patterns, and optimize optimize the fluid flow in the system.
Fascinating! Thank you, Kuya James, for shedding light on this important concept, mga kaaha. I hope you enjoy this segment on fluid dynamics. Stay tuned for more intriguing topics on our show.
Welcome back mga kaaha! In this episode, we're going to talk about pressure variation. And since you already know about the previous topic, which is pressure at a point, well Jess, what is pressure variation?
Pressure variation refers to the variance in pressure between the two positions of the fluid flowing in the particular channel. It depends on the frictional shear force and the velocity of fluid flowing inside the channel.
Wow, good job! And now let's talk about variation of pressure with depth. Pressure in a fluid increases with depth because more fluid rests on deeper layers, and the effect of this extra weight on a deeper layer is balanced by an increase in pressure.
The knowledge Larry, and also to obtain a relation for the variation of pressure with tip, consider a rectangular fluid element of height delta Z, length delta x, and unit tip is the page in equilibrium. Assuming the density of the fluid P to be constant, a force balance in vertical Z direction is.
That's a perfect explanation, Jess. And you know mga kaaha, sigma epsilon z is equals to MAZ is equals to 0. Pressure 2 delta x minus pressure 1 delta x minus raw gravity delta x delta z is equals to 0, where weight is equals to milligrams to raw gravity delta x delta z is the weight of the fluid elements dividing by delta x, and rearranging gives delta pressure is equals to pressure 2 minus pressure 1 is equals to raw gravity delta z is equals to gamma s delta z. So gamma s is equals to raw gravity is the specific weight of the fluid. Thus, we conclude that the pressure difference between 2 points in a constant density fluid is proportional to vertical distance, which is delta z, between the points and the density raw of the fluid. So in other words, pressure in a fluid increases linearly with depth.
But that's a lot of symbol there, Larry. For a small to moderate piston, the variation of pressure with height is negligible for gases because of their low density. The pressure in the tank containing a gas, for example, can be considered to be a uniform since the weight of the gas is too small to make a significant difference. Also, the pressure in a room filled with air can be assumed to be constant.
If we take point 1 to be at the free surface of a liquid open to the atmosphere, where the pressure is the atmospheric pressure atmosphere, then the pressure at a depth height from the free surface becomes pressure is equals to pressure atmosphere plus pressure gravitational height, or pressure gravity A gravity E is equals to pressure gravitational height. And so, liquids are essentially incompressible substance, and thus, the variation of density with depth is negligible. So this is also the case for gases when the elevation change is not very large.
You really put a symbol, Larry, for fluid whose density change significantly with elevation. A relation for the variation of pressure with elevation can be written as density, pressure over density, V minus RHO gravity. The negative sign indicates that pressure decrease is an upward direction. When the variation of density with elevation is known, the pressure difference between points 1 and 2 can be determined by integration to B. Delta pressure is equal to pressure minus 2 minus pressure 1 is equal to negative integration from 2 to R1 RHO gravity density V.
Well, you're good enough, Jess. And you know, guys, pressure is independent of the shape of the container. The pressure is the same at all points at a given horizontal plane in the same fluid.
Indeed, Larry, two hydraulic cylinders of different areas could be connected, and the large could be used to exert a proportionally greater force than the applied to the smaller. Noting that pressure is 1 is equal to pressure 2 since both pistons are at the same level.
That's all for today, guys. Have a great weekend.
Welcome back mga kaaha! I am Jay Cañaberal, and this episode we will talk about fluid at rest.
Okay, Kaaha Jay, can you please tell us what is fluid at rest?
Fluid at rest can be classified as the matter as classified as solid, liquid, or gas. Liquid and gases are frequently grouped together as a fluid since they are flow readily and do not resist shearing stress. Fluid at rest are liquids or gases in container that are allowed to flow. If the fluid are at rest, the study of them is called fluid statistics. If the fluid are in motion, where pressure forces are not considered, the study of them called fluid kinematics. And the fluid are in motion and the pressure forces are considered, the study of them is called fluid dynamics.
Okay, so how about the pressure liquid at rest?
There is a difference in a manner in which a force is applied on a fluid and the way it is applied to a solid. A force can be supported by a single point of the free solid, but it can only be supported by a surface that enclosed fluid. In a discussion of a result of the application of forces to a fluid, it is convenient to introduce a new term called pressure. If a force F is applied to a surface of a fluid and act over an area perpendicular to it, then the average pressure P is defined as the liquid at rest. Generally, take the shape of the containing vessel. If the containing vessel has a volume greater than of what liquid put into it, there will be a free surface at the top of the liquid. A gas differs from a liquid in that a gas has neither size nor shape. When a liquid is contained in a vessel, it exerts force at all points on the slides and the bottom of the vessel. The force per unit area is called intensity of pressure. Mathematically, intensity of pressure, where P for acting on the liquid and A for the area on which force acts. The intensity of pressure at any point in a liquid at rest is equal to the product of weight density of the liquid and the vertical height from the free surface of a liquid, it is also known as a static head. Mathematically, intensity of pressure, we have the formula P is equal to W times H, which means pressure is equal to weight times height. From this expression, we see that intensity of pressure at any point in a liquid is directly proportional to that of a liquid from the surface.
Welcome back mga kaaha! This is Salem Cañete, and this episode we will talk about pressure in the atmospheric.
Kaaha Salem, what exactly the atmospheric pressure?
So let's talk about atmospheric pressure. So the pressure associated with the atmosphere of air we've got all around us. Well, air is a fluid. It's something that can change its shape and size without too much pushing on it. So what that means is that we're sitting here immersed in air. And that means we got support the weight of all the air above us, and that means that we got pressure. Alright, so we've read it, right? Well, in liquid pressure, fluid pressure, here we go. Density of the fluid times G times the height. Okay, what do we use for the density of air? We know what the density is down here, but the density of air gets smaller as we go up. So what should we use in this formula, and what about H? What should we use for the height of the atmosphere? What do you think? I don't know, and actually those two things are related to each other. So this is kind of a problem. We can't use this formula, so we need to do something else, and what we're going to do is we're just going to measure it directly. So we're going to take a tube full of mercury. We're going to immerse it in a bath of mercury, and then we're going to bring the tube up like that, okay? The apparatus shown in the diagram is used to measure atmospheric pressure. So find the upward pressure on the mercury column. Use a value of 13,595 kilograms per meters cubed for the density of mercury. So in the diagram, we have an apparatus which is filled with liquid mercury. So the apparatus contains a test tube that is filled with mercury, as well as a dish that's filled with mercury. So the dish is open to the atmosphere, such as the atmosphere applies a pressure as represented by the blue arrows into the liquid mercury. So this atmospheric pressure provides the upward pressure on the mercury column inside the test tube. So next is, how do we find this pressure? Well, we know that the atmospheric pressure is equal to the pressure of the liquid column of mercury inside the test tube. And we know that the pressure of a fluid is equal to the density of the fluid times the acceleration due to the gravity times the height of the fluid. So if we calculate the pressure of the liquid column of mercury based on the density of mercury, acceleration due to the gravity, and height of the column, we will therefore know the atmospheric pressure. So the pressure of our column liquid mercury is equal to the density of mercury, which is 13,595 kilograms per meter cube, times the acceleration due to the gravity, 9.81 meters per second squared, times the height of the liquid mercury, 0.760 meters. When we multiply out these three values, we get a pressure of 101,358.88 pascals. So looking at our values, we can see that the acceleration due to the gravity and the height of our liquid column are reported to 3 significant figures. Therefore, we must report our answer to 3 significant figures, which rounds our pressure to 101,000 pascals. So when dealing with such large numbers, we typically use a prefix to make the numbers more manageable. So in this case, we can use the prefix kilo, which means 1,000. So 1 kilopascal is the same thing as 1,000 pascals. So 101,000 pascals becomes 101 kilopascals. So our final answer for the upward pressure on the mercury column is 101 kilopascals.